is Mike Gianfagna speaking. I'm the Vice President of Marketing at eSilicon Corporation, and welcome everyone to our webinar entitled High Performance Communications Delivered. We're going to discuss today sort of a case study in what it takes to deliver high performance communications. It turns out it's a team sport. It requires multiple companies and multiple disciplines. You'll hear first from Dan from SemiWiki, who will give you an introduction and an overview to some of the trends that are driving this need for higher and higher high performance communications. You'll then hear from Al from Wild River about the actual design of a rather sophisticated test board that helps to deliver that high performance communication into the customer's system. Matt from Samtec will talk about the connectivity and the cabling required to support that communication. And then finally, Tim from eSilicon will pull it all together and explain how our high-performance SerDes is inserted in that board and becomes the engine, if you will, to deliver the required performance. So that's the timeline we'll follow today. So with that overview, I'm going to pass it over to Dan Nenny from SemiWiki.com, who is going to kick it off and tell us a little bit about industry trends.
Thank you, Mike. As he said, I'm Daniel Nenny, a career semiconductor professional for more than 35 years, and I'm your moderator today. In 2011, I founded SemiWiki.com, an open forum for semiconductor professionals. We currently have more than 40,000 registered members. If you're not already a SemiWiki.com member, please join as my guest. I hope to see you there. According to an IDC white paper sponsored by Seagate, the global datasphere will grow from 32 zettabytes in 2018 to 175 zettabytes by 2020. 1 zettabyte is 1 trillion gigabytes, by the way. This white paper also reports that today more than 5 billion consumers interact with data every day. By 2025, that number will be 6 billion, or 75% of the world's population. Every person is predicted to have at least one interaction with this data every 18 seconds. Furthermore, if you try to download the entire 2025 global datasphere at an average speed of 25 megabytes per second, which is today's average connection speed across the United States, it would take one person 1.8 billion years to do it. So that's a lot of data. This rise in data volume and interaction with the data is why we're here today. Designing a new high-speed communication technology requires robust test hardware. This is how new systems are validated. There are at least two fundamental challenges associated with this kind of test hardware. First, performance must be delivered in its purest form with as little influence as possible from the test hardware being used. Second, the designer must be able to accurately measure what performance they're getting across many scenarios. Only after the true performance of the system can be measured this way will the designer know if they've delivered what's needed. We'll now explore these and other challenges associated with meeting the future demands of our exploding datasphere. Our first speaker is Al Neves from Wild River Technology. Off to you, Al.
Hello, my name is Al Neves. I'm the Chief Technical Officer at Wild River Technology. Wild River Technology is, we do a combination of standard products and services. And one of the key services that we provide our customer base, this next slide, is test fixtures. If you look at the dark blue test fixture, we designed that. We designed that in cooperation with both Samtec and eSilicon. When you're designing a really difficult and very challenging test fixture, for example, 56 gig PAM4, you want to have three things down before you actually start doing designing the fixture. You want a clear methodology, fabrication, de-embedding, signal integrity. You want to have very clear signal integrity metrics. The technical manager wants to drive the group very cleanly and have unimpeachable SI metrics. You also want to benchmark your tool and have your tool tuned. You want to know how to use your EDA tool very well. You also want to be able to identify all the critical crux elements in your system. What's difficult? So remember that blue platform that's sort of in the middle? That was at the Samtec booth at DesignCon, and we designed that. The next slide. So what could go wrong with that platform? I call it the Alamo strategy. We built a second platform in conjunction with the test platform that allows us to mitigate risk. It also allows us to do some advanced de-embedding and also allows us to do characterization of jitter for the SerDes. So there's a companion channel modeling platform that was created that allows us to look at individual elements from the test platform. Now, let's talk about what exactly is, I mentioned this, what exactly is good signal integrity? There's a group, next slide, there's a group, IEEE group P370 that's done a lot of work. They've done it to 50 gigahertz. This particular platform was designed to 50 gigahertz. We're releasing a 70 gigahertz platform actually this next week. One of the key metrics that's discussed in IEEE P370 is what exactly is good signal integrity. This is an example of good signal integrity or metric where you have separation between the insertion loss and the return loss. That separation is a key metric in the frequency domain. Next slide. One of the metrics we use internally at Wild River Technology, we use the fastest TDR that we can get our hands on, and we slam our system with that TDR, and then we do an impedance profile, and then we look at what the maximum bump is. And our internal objective is to get less than 2 ohms bump for the impedance throughout the system, and that includes everything. We're coming up to a momentous time in history. July 20th, 1960. I was a mere lad of 9 years old. Man landed on the moon. American landed on the moon. So one of the things that we can learn a lot from the Apollo on how they manage things technically, on how to manage signal integrity projects. One of the key things that they did is they had 3 independent teams that often worked on crux elements of the system. And in the specific case, you had 3 different teams that were working on trajectory. In our case, I managed the 3 teams. I was the technical manager, and I had 2 HFSS teams. One of them was at one of them was at Samtec rather, and then using HFSS. Then we had an internal HFSS team, and then we also had a SemiWiki team at Wild River Technology, and created the green template based upon the requirements of doing some PAM4 work. And we drove the team to improve the optimization so it was less than the green line in terms of return loss. And that was their target optimization, their EDA tool. This worked out really, really well. One of the other crux elements, next slide, was the high density interconnect, which was the bullseye connector. You need a lot of channels coming out of the serial link. And what we're finding is the whole connector thing is problematic. The views that I'm expressing are the views of Wild River Technology, since I own the company. And the connector companies need to do a better job. They're very powerful. They're in all the standards committees. And when you start asking for test fixtures, measurements, really good models of the connectors, all the tools that you need to do high confidence 50 plus gigahertz design, our impression is that the industry needs to do a lot better. So we started to work with Samtec, and we were happy with the response that we got, and things worked out really, really well for us. I'm not going to get into the detail on all of this, but you should push your connector vendor, especially when you're going past the 50 gigahertz and you're doing things like 56 gig PAM4. An example of the test fixture that they provided us that we reviewed was the next slide. Clearly shows, based on IEEE P370, that they achieved some pretty stellar signal integrity metrics. We were really happy with their test fixture. That looks really, really clean. So there's a lot of elements that need to come into play. Companies need to work together, and you have to identify your crux issues, and you have to have real clear signal integrity metrics in your system. I'd like to turn the conversation over to Matt Burns, who's a technical marketing manager at Samtec. Thank you.
Thanks, Al, for that setup and that nice review. As Al mentioned, Samtec is a global broadline manufacturer of a large number or a large variety of interconnect solutions, ranging from high-speed board-to-board, high-speed cable, optics, and flexible stacking and micro rugged. For our presentation this evening, we're going to focus in on the flagship solution that Samtec offers through our Precision RF product portfolio, our Bullseye high-performance test system. Bullseye really evolved out of working with leading IC suppliers like eSilicon, specifically for the need for test applications in IC characterization. As SerDes channels increases, the number of channels, the number of SMA connectors has also increased. In some instances, we work with IC vendors that require dozens, if not hundreds, of RF connections on their IC characterization boards using traditional SMA, PCB mount SMA technologies while they work are very bulky, very expensive. So we've developed the Bullseye test point system as a SMA replacement technology for IC characterization and other test platforms like this solution that's been developed between eSilicon, Samtec, and Wild River. Some of the key features of the Bullseye platform are illustrated in some of the graphics here. There's a compression interface, which makes it easy to attach to PCBs. It also has a small footprint, a small footprint that also saves space on your PCB. You can see the illustration there in the center of the slide. Bullseye provides a 4-to-1 space savings on the PCB compared to traditional SMAs. It's also a very rugged interconnect because it has high cycle counts. So the bulkhead and the cables can be connected numerous times without failure. And it also is very versatile in terms of the PCB layout, supporting both microstrip and strip-line PCB transmission. A lot of work has also gone into the cable. You can see from the illustration there on the bottom that there are solid center conductor cables with low value dielectric material. There's a triple grounding scheme within the solution. And when you tie all these systems together, or tie all these features together, it really promotes high performance in high frequency test applications such as what we're discussing this evening. Next slide, please. Al mentioned also the importance of having good models. And one of the ways that Samtec, or many of the ways that Samtec is able to support that in working in high frequency and high performance communication applications is by using the leading tools in the industry. Similar to Wild River, Samtec also uses world-class simulation engines, especially the ANSYS HFSS, not only for simulating and designing the connector, but also modeling it at a system level. We backed it up by using our high-performance computing cluster, which really enables us to drive the accuracy of the tools to below achievable manufacturing tolerances. In addition to building good models for our connectors and for our cable assemblies, we also realize that we have to simulate those in a real-time environment. So not only is it looking at how the connector performs, but how it performs once it's attached to a PCB. And we really adopt that same channel methodology that Al mentioned to simulate the connector, the cable, and the PCB together. We also have a good understanding of electromagnetic principles between the connector and its attachment to the PCB. So not only is that understanding the electromagnetism of the signals passing through the interconnect, but it's also looking at the physics of the PCB material, whether the laminates, the symmetry, understanding how they work together, as Al mentioned in his solution, to make sure that we're optimizing the performance of the interconnect on the particular platform. So how did that work within the eSilicon Wild River Samtec solution? The graphic that we show here highlights in red the return loss mask that Al asked the 3 teams to hit. And you can see that the connector and the breakout region that we have on the PCB had a return loss well below the mask that Al set up, all the way out to 70 gigahertz. So this is a very robust, very high performance interconnect solution for 56G PAM4 and soon to be released 112G PAM4 solutions. Next slide, please. In addition to simulating and testing and measuring the interconnect attached to the PCB in the breakout region, we also want to be able to achieve optimal performance across the cable. So some of the things that we were able to work on to optimize the performance across the system was optimizing the breakout region or the launch of the connector within the PCB. We actually saw a picture of that on the previous slide. We also work on optimizing the breakout so that we minimize variation sensitivity across manufacturers. We know that there's many PCB board houses that OEMs use. So we work really hard to understand what the leading PCB vendors' capabilities are, and then we try to do the best we can to minimize variations in our model from vendor to vendor. Additionally, we mentioned earlier that Samtec has a lot of experience working with Bullseye. So we have field-based resources, our SI resources, and we have a tremendous amount of speedway, if you will, or runway with working with Bullseye and high-performance solutions as this platform. So the results, this is actually showing a 150 millimeter long BE48 cable. You can see a return loss on the cable of less than 4 dB, excuse me, an insertion loss of less than 4 dB out to 40 gigahertz, a return loss of roughly 15 dB, and then a VISWAR of less than 1.5 all the way out to 40 gigahertz. Next slide, please. So what's next? We've shown that we can simulate the connector PCB junction at 70 gigahertz. We've shown good performance with a 40 gigabit cable, excuse me, a 40 gigahertz cable. What about 70 gigahertz? Al mentioned that the existing solution, the eSilicon Samtec Wild River solution, was displayed at DesignCon this past January, and we're getting ready to release a 70 gigahertz version in the very near future. So what are the things that Samtec has done to make sure that our cables, our Bullseye cables, work in that frequency range? Well, again, it's not just a matter of making engineering changes to the solution to make it work. It's really a collaboration between the three companies, and our SI team working with the Wild River team are also working with the eSilicon team to essentially co-develop, co-engineer the Bullseye solution. That has really enabled us to have an evolution of the connector and the breakout region on the board. So we've been able to fine tune it based on what we've learned through simulation and testing. And then lastly, we also have the application engineering support through our field-based teams to offer the SI and our SI teams to offer the support necessary to get the performance that's required in the application. From a feature standpoint, moving from BE48 to BE70A, some of the material improvements that we're making are going to a higher precision 1.85 millimeter N2, which attaches to the PCB. We're using a smaller, higher performance cable, and we're moving from a pogo pin contact design on the current BE40A to a spring-loaded outer contact on the BE70 version. So all of these features combined to make Bullseye 70 gigahertz version the market-leading solution for high-performance communication test fixtures, as we've demonstrated with eSilicon and Wild River. Our next speaker is Tim Harrell, and he will provide the details about how we tie this system together. Tim?
Hi, thanks, Matt. My name is Tim Harrell, and I'm Director of Field Applications here at eSilicon Corporation. eSilicon is primarily an ASIC provider in the networking and data center, telecom, datacom type space, and moving into AI. And part of what we do is to enable that portfolio for our customers is generate differentiated IP. One of those key IP development efforts has been in the SerDes area. And that's primarily what we'll be talking about in the next few slides. So starting on the SerDes area, one of the key things is the modulation of the pulse that's being delivered through the interconnect. One of the key limitations in terms of how much signal you can get through is a function of the operating frequency. PAM4 allows you to send twice as much data with the same frequency limitations that the NRZ or PAM2 type of modulation would provide. But it comes with some issues. The PAM4 reduces the spacing by a factor of 3, because now you've got 4 signal levels. And what that does is it lowers your signal-to-noise ratio considerably, and that adds significantly to the design requirements of the receiver. There has to be quite a bit of improvement in the receiver design over what would support a typical NRZ type of interface. So what ends up happening is that the PAM4 signaling is easier to apply in the shorter reach channels where signal-to-noise ratio improvements are much easier to get in the hardware. Part of what we've done in this design is help people break that barrier, making the PAM4 signaling methodology useful for very long runs. So looking forward, at 112 gig, rather than produce a simple 4-lane test chip, we're doing a full ASIC that is a complete implementation of a 400 gig Ethernet gearbox retimer. It's targeted primarily as data center, 5 gig, and optical networking applications. In terms of the IP itself, we have 8 lanes of 56 gig SerDes and 4 lanes with 112 gig design. And we've partnered with Precise ITC to provide the FEC, gearbox, and PCS layers for the device. We now expect silicon back in early 4th quarter. And we expect to be out with public demonstrations and evaluations by the end of the year. This chip really demonstrates the capabilities that we have for full long reach and low power. To give you an example, there's only 4 watts for all of the SerDes lanes running at full reach and max data rate. The IP that we selected in terms of a partner for the PCS and FEC are very low latencies for time-critical applications. For example, the types of constraints you find in high-performance computing. And it indicates how you can do full integration of the complex third-party IP with our SerDes. This includes complete development of a typical I/O frame that goes along with it. And these include the critical subsystems that our customers have told us that they care about in a test chip design, which is the FEC, primarily with the SerDes. So from that perspective, we need a seriously good evaluation platform. And this requires multiple capabilities from the customer perspective. Part of what we have to have is that it be easy to use and a fully capable software interface so that all of the features within SerDes can be accessed in an optimal way. We need fully characterized interconnect so that we can do de-embedding as is required by all of the latest standards. And on top of that, we need the lowest possible IL so that we can maximize the externally available insertion loss for the channel applications that our customers want. And that latter piece is what's driving the requirement for really high density cable connector sets, such as the Samtec rings. The reason we pulled that in. And the reason that we're doing all of this in partnership with Wild River and Samtec is because the combination of the two has provided us with the highest quality signal integrity analysis groups that are available in development area and full platform design capabilities. So this also allows us to maximize the use of the developing standards that are available in the IEEE, such as the P370 that Al mentioned, and the leading edge connector technology that Samtec has provided and the support for the development has allowed us to provide an optimized solution for both the 58 and the 112 gig SerDes for full characterization and evaluation. So we're quite pleased with the result and are looking forward to having the boards in our hands in a couple of weeks.
So I'll take over now, and this is Mike speaking. And thank you for your questions. Any other questions you have, feel free to type them in the chat window, as I mentioned. But questions that we received so far. To start with, we received a question for Al at Wild River. How do you improve serial link reach?
So that's really a good question. Thank you for whoever asked that question. First of all, reach is You have a SerDes. I'm sure that Tim Harrell could elaborate on this with quite a bit more detail than I can. But from a high level perspective, reach is I have a transmitter that's driving a channel. The channel has a certain length, and the receiver is receiving it, and you're doing all the equalization, and you want a fairly open eye at the other end. How long can the channel before the eye starts to get too closed? Might be actually good to get some input on what too closed is. So having said that, channel impairments will close the eye down. Channel impairments include dielectric skin effect losses and losses due to the metal or surface roughness. So certainly using a low loss material is advantageous. Traditional materials are about 0.076 gigahertz per inch. Some of the newer materials from Isola or Panasonic are closer to 0.06 dB per loss per gigahertz per inch. So you can do some simple calculations, and it's relatively linear, and find out what your reach is in terms of the number of inches. And of course, PAM4 and NRZ looking at the reach and equalizing the channels. One of the key things that people neglect is they try to go right for the lowest loss channel. Okay, lowest material, the best material, the lowest loss material that they can get. And what happens often is if their design's not, if they're not on their A game on their design, they have return loss issues, and that can get exasperated as you have less loss. So the low loss material actually can hurt you. So what will happen is you'll have return loss that degrades the reach of the system. So you need two things. You need low loss material, and you also need a test fixture or backplane with really low return loss, so the energy is not reflected. Think of the Hubble telescope. You know, they put this telescope in space and they got it out of the atmosphere because light was reflecting off the atmosphere. It's a very good analogy for looking at return loss in the system.
So a question for Matt at Samtec. What are some typical applications where bullseye is used?
I guess that's a good question. As we've shown in this webinar, Bullseye has a long history in IC test platforms, whether that's IC characterization or test fixtures. We also see them in a variety of IC evaluation development platforms, especially where high speed and high density is needed, such as SerDes applications and other similar IC solutions. We're also starting to see interest within the 5G ecosystem, again, because of the density and performance needed for all the RF signal chain in those types of products.
Okay, thank you. So I think we'll finish off the evening with a question for Tim at eSilicon. So the question is a little bit of a long one, but what is the total power dissipation for the full length? That is the SerDes, the DSP, the ADC, the DAC, with PAM4 for each data rate at 56G and 112G.
That's kind of an interesting. On the power numbers that we quote are for a fully complete hardened macro. So all of the SerDes elements that are mentioned in this question are already included in the power numbers that I mentioned before. So it's 4 watts for a total of 8 lanes of 56 gig and 4 lanes of 112 running at the maximum data rate with full reach. So these are fully activated designs. So and since this is roughly 50-50 to first order, you're seeing about 2 watts for 8 lanes of 56 gig and 4 watts, 2 watts again for the 112 gig 4 lanes. So that's roughly a 1/4 watt per lane transmitter plus receiver on the 56 gig and roughly a 1/2 watt per lane with all in on the 112 gig.
Okay. All right, thank you. Okay, those were some good questions. Thanks for those submissions, and thank you for joining us on this webinar. We'll stop here, and I'll just remind everyone that they will be getting the white paper Anyone who views this webinar will be able to download the white paper, and that will be coming very soon to your inbox. So thank you, everyone, and we'll conclude here. Have a good day.